What if everything we think we know about the universe is just the tip of the cosmic iceberg? Picture this: somewhere beyond the edges of our telescopes, beyond the faintest glimmers of distant stars, lie realms so strange they defy all logic. Places where time twists backward, where ancient civilizations might have left echoes among the stars, and where entire worlds could be hiding in plain sight, just waiting to be discovered. These aren't the plots of science fiction. They're real mysteries lurking in the uncharted territories of our cosmos, and today we're setting off to explore them together. Think about the last time you stared up at the night sky, feeling that tug of wonder. That's the same pull that has driven explorers, both ancient and modern, to chase the unknown. From the earliest astronomers mapping constellations to the scientists decoding signals from the depths of space, humanity has always been drawn to the enigmas of the universe. But here's the thrilling part. We're living in an era where those mysteries are closer to being solved than ever before. New telescopes peer deeper into the void, uncovering celestial oddities that rewrite the rules of physics. Lost worlds, once thought to be myths, are now being hunted in the data streams of satellites, and the deeper we look, the more we realize how much is still out there, waiting. This journey isn't just about distant galaxies or bizarre cosmic phenomena. It's about what these discoveries say about us. Every time we uncover a new piece of the puzzle, whether it's a rogue planet drifting between stars or an ancient signal from a long-dead star, we're not just learning about the universe. We're learning about our place within it. What if the answers to life's biggest questions are hiding in these uncharted territories? What if the next great discovery isn't just about finding something new, but about realizing we were never alone in the first place? Strap in, because we're about to venture into the cosmic unknown, where the stories are stranger than fiction, and the truths, well, they might just change everything. Right now, you're looking at a cosmic map that's still half-finished, like an ancient explorer's parchment with entire continents left blank. But these aren't missing land masses. These are voids where our instruments go blind, where the known laws of physics start to fray at the edges. Take dark matter, for instance. It makes up nearly 27% of the universe, yet we've never seen it directly. It's like trying to map a city by only hearing the echoes of footsteps in empty streets. Then there are rogue planets drifting between stars without a sun to call home. Imagine a world in perpetual twilight, where oceans could be frozen solid or bubbling beneath icy crusts untouched by starlight for billions of years. And the strangest part, some of these uncharted territories might be closer than we think. Just last year, astronomers detected odd radio circles in space, gigantic, ghostly rings that defy explanation. They could be shock waves from cosmic collisions, or something far more mysterious. It's not just about what we might find out there, but how these discoveries could rewrite the story of our own existence. What if dark energy, that mysterious force accelerating the universe's expansion, isn't just a cosmic quirk, but a sign of dimensions we can't yet perceive? The beauty of these blank spots isn't just their secrets, it's how they humble us. Every time we build a better telescope or a faster probe, the universe seems to say, wait, there's more. And that's the thrill of the chase. Whether it's a hidden ninth planet tugging at the edges of our solar system, or whispers of parallel universes in the cosmic microwave background, one thing's certain: the greatest discoveries in science often start with a simple admission. We don't know, but oh, we're getting closer. Lost worlds don't just vanish, they leave clues behind, like cosmic breadcrumbs waiting to be followed. Take the curious case of the star catalogued by ancient Greek astronomers over 2,000 years ago. They recorded a bright object in the constellation Scorpius, a star so prominent it earned a name, Antares B. Yet today, our telescopes find no trace of it. Did it explode, collapse into a black hole, or simply dim into obscurity, its light fading like an ember in the wind? This isn't just a missing star, it's a mystery that challenges our understanding of how celestial objects behave over millennia. Then there are the planets that slipped through our fingers. In the early 20th century, astronomers were convinced a massive world, dubbed Planet X, lurked beyond Neptune. Percival Lowell spent years chasing it, and while Pluto eventually turned up, it wasn't the giant he expected. Decades later, we're still uncovering dwarf planets in the Kuiper belt. Could the real Planet X still be hiding among them? Or perhaps it was never there at all, a cosmic ghost story born from miscalculations and wishful thinking. But the most haunting lost worlds aren't just misplaced, they're erased. Imagine a planet orbiting a star that goes supernova. One moment, it's there, a world with mountains, oceans, maybe even life. The next, it's vaporized in a blast of radiation, leaving no trace except a ripple in space-time. Or consider rogue planets flung from their solar systems by gravitational chaos. These nomads drift through the galaxy, invisible to us unless they pass in front of a distant star, bending its light like a cosmic mirage. And what about whole galaxies? In 2018, astronomers discovered a galaxy called NGC 1052DF2, which seemed to defy the rules. It had almost no dark matter. Then, just a few years later, another team argued it might not exist at all. Its strange readings just a trick of perspective. It's a reminder that even the mightiest structures in the universe can be illusions, flickering in and out of our understanding. The search for these lost worlds isn't just about filling in blanks on a map. It's about realizing how fragile our knowledge really is. Every time we think we've pinned down the universe, it reveals another layer of secrets, worlds that vanish, stars that defy their timelines, galaxies that shouldn't exist. Maybe that's the most thrilling part. The cosmos isn't just hiding answers, it's asking us better questions. Somewhere in the vast expanse of the universe, an invisible force is playing tug of war with entire galaxies and winning. It's called the Great Attractor, and it's one of the most baffling puzzles in modern astronomy. Picture this: millions of galaxies, including our own Milky Way, are being pulled toward a single point in space at over 600 kilometers per second. That's like racing from New York to Los Angeles in just 6 seconds. But here's the catch: we can't even see what's doing the pulling. The Great Attractor lurks in a region astronomers call the Zone of Avoidance, a cosmic blind spot obscured by the thick dust and stars of our own galaxy's disk. It's like trying to spot a lighthouse through a thunderstorm. Early observations suggested it might be a supercluster, a dense knot of galaxies bound together by gravity. But as our telescopes improved, something didn't add up. The pull was too strong, too concentrated. Could it be a colossal black hole, far larger than anything we've ever detected? Or is it something even stranger, a structure or force we don't yet have the physics to explain? What makes this mystery so tantalizing is how it challenges our understanding of the universe's architecture. Gravity, as we know it, shouldn't be able to yank galaxies so forcefully over such vast distances. Some theorists speculate the Great Attractor might be just the tip of an even larger cosmic iceberg, a signpost pointing to something beyond, like the shadow of a supermassive cluster we can't yet see. Others wonder if it's evidence of exotic phenomena, like dark energy's uneven influence or wrinkles in spacetime itself. The hunt for answers is pushing our technology to its limits. Infrared telescopes pierce through the dust of the Zone of Avoidance, revealing glimpses of hidden galaxies. radio arrays map the invisible tendrils of dark matter that might be weaving this cosmic web. And every new observation adds another piece to the puzzle, even if it's a piece that doesn't quite fit, because that's how discovery works. The universe doesn't hand us tidy answers. It dares us to ask better questions, and somewhere in the darkness, the Great Attractor waits, reminding us that the cosmos still holds wonders beyond our wildest imagination. Imagine the universe as a river, not just any river, but one where entire galaxies are swept along by a current we can't see. This is dark flow, one of the most perplexing cosmic mysteries of our time. While the Big Bang Theory predicts that the universe should expand uniformly, like dots on an inflating balloon moving apart evenly, astronomers have spotted something strange. Clusters of galaxies aren't just drifting, they're racing toward a single point beyond the edge of our observable universe, as if pulled by an invisible hand. The numbers behind this motion are staggering. These galaxy clusters are moving at speeds exceeding 1,000 kilometers per second, far faster than standard cosmic expansion can explain. It's not just a few outliers, the pattern spans billions of light years, suggesting a force vast enough to tug on the fabric of the cosmos itself. But here's the twist, there's nothing there. No supercluster, no black hole, no known structure powerful enough to generate this pull. Just empty space, or at least what looks like empty space to our instruments. So what could be causing it? One radical theory suggests dark flow might be the gravitational fingerprint of another universe beyond our own. Think of it like a cosmic neighbor pressing against the fabric of space-time, creating a dent that our galaxies are sliding toward. Others propose it's evidence of exotic matter, something even stranger than dark energy woven into the universe's structure. Then there's the unsettling possibility that our models of cosmic expansion are incomplete, missing a fundamental piece of the puzzle. The implications are profound. If dark flow is real, it could rewrite our understanding of the universe's boundaries. Are we seeing the first hints of a multiverse, or is there a colossal structure lurking just beyond our observational horizon, invisible to our telescopes? Every new survey, from the Planck satellite's cosmic microwave data to next-generation space telescopes, brings us closer to an answer. But for now, dark flow remains a tantalizing enigma, a reminder that the universe still holds mysteries too big for our current science to contain. And that's what makes it so thrilling. The unknown isn't just out there, it's pulling us toward it. Imagine a world without sunrises, where the sky is forever black and the only warmth comes from deep within the planet itself. This isn't science fiction, it's the reality for rogue planets, the cosmic nomads adrift between the stars. Unlike the planets in our solar system, these wanderers don't orbit a star. They were either flung from their home systems by gravitational chaos or formed alone in the cold depths of interstellar space, and they're far more common than you might think. Recent estimates suggest there could be billions of them silently moving through our galaxy, unseen and untethered. What makes these rogue planets so fascinating isn't just their loneliness, it's what they might hide beneath their frozen surfaces. Take Europa, one of Jupiter's moons, as an example. Even in our own solar system, we've found worlds with vast subsurface oceans, kept liquid by the heat of tidal forces or radioactive decay. Now picture that on a rogue planet where an icy shell miles thick could shield a hidden sea from the vacuum of space. In that eternal darkness, shielded from radiation and stellar flares, life might find a way. Not as we know it, perhaps, but as something adapted to the endless night, organisms thriving in chemosynthetic vents or drawing energy from geothermal heat. But how do we even find these invisible drifters? Without a star's light to reflect, rogue planets are nearly impossible to spot directly. Instead, astronomers hunt for them using a cosmic trick of the light. When one of these dark wanderers passes in front of a distant star, its gravity bends the starlight like a lens, creating a brief flash in the sky. These microlensing events are fleeting, lasting only hours or days, but they've already revealed dozens of rogue planets, some as close as a few dozen light-years away. And here's the real twist: some of these worlds might not be icy wastelands at all. A rogue planet with a thick hydrogen atmosphere could trap enough heat to maintain surface temperatures far above freezing, even without a sun. Imagine a world where the sky glows faintly from internal heat, where geothermal vents create oases in the dark. It's a reminder that life, if it's out there, might not need a star to survive, just the right conditions beneath the surface. The more we learn about these nomadic worlds, the more they challenge our understanding of how planets form and evolve. Were they ejected from young solar systems during planetary billiards, or did they coalesce from lonely clouds of gas and dust? Each discovery peels back another layer of mystery, hinting at a galaxy far stranger and more diverse than we ever imagined. And who knows, the next rogue planet we find might not just be a frozen relic, it could be a world teeming with secrets waiting in the dark. The silence of the cosmos isn't just puzzling, it's deafening. With billions of galaxies, each brimming with stars and planets, the universe should be a cacophony of civilizations. Yet all we hear is static. This is the heart of the Fermi paradox, a question that's haunted scientists for decades. If life is so likely, where is everyone? The answers might be hiding in the uncharted territories we've only begun to explore. Consider the sheer scale of time. Earth has existed for 4.5 billion years, but human civilization. A mere blink in cosmic terms. Advanced alien societies could have risen and fallen millions of years before the first pyramids were built, leaving behind nothing but faint echoes, radio signals long dissolved into noise, megastructures eroded by stellar winds, or planets scoured clean by their own inhabitants. The universe might be littered with the ruins of civilizations we'll never know, their stories lost to the abyss of deep time. Then there's the possibility that we're simply not listening the right way. Our search for extraterrestrial intelligence has largely focused on radio waves, a technology we've used for barely a century. What if advanced civilizations have moved beyond such primitive methods? Imagine a society communicating through neutrino pulses, quantum entanglement, or some medium we haven't even discovered yet. It's like trying to spot a smartphone with a telegraph receiver. Or perhaps they're hiding. The dark forest hypothesis suggests that in a universe teeming with life, staying silent might be the only way to survive. Any civilization that broadcasts its location risks attracting predators or rivals, so the smartest move is to stay invisible. If that's true, the cosmos isn't empty. It's a vast, silent game of hide and seek, with every player holding their breath. But here's the most tantalizing idea. What if we're looking in the wrong places entirely? Our telescopes scan the habitable zones of stars, searching for planets like Earth. Yet life could thrive in environments we'd never consider, floating in the atmospheres of gas giants, burrowed in the icy crusts of moons, or even riding the cosmic rays between galaxies. The universe's greatest civilizations might not be on planets at all. They could be out there right now, hidden in plain sight, waiting for us to think beyond the limits of our own imagination. The Fermi paradox isn't just a question about aliens, it's a mirror. Every possible answer tells us something about ourselves, our fears, our hopes, and the fragility of our place in the cosmos. Whether the silence means we're alone, outmatched, or simply not listening hard enough, one thing's certain: the truth is out there, and it's stranger than we've dared to dream. One day in October 2017, astronomers spotted something that shouldn't have been there, a needle-shaped object tumbling end over end through our solar system at blistering speeds, so fast it could only have come from another star. They named it Oumuamua, Hawaiian for scout, and in that moment humanity got its first confirmed visitor from interstellar space. But this was no ordinary space rock. The more we learned, the stranger it became. For starters, its shape defied logic, long and thin, like a cosmic cigar, stretching nearly a quarter mile in length but only a tenth as wide. Nothing in our solar system looks like that. Then there was its movement. As Oumuamua swung past the sun, it didn't just coast, it accelerated, as if pushed by some unseen force. Comets do this when their ices vaporize, creating a gaseous tail. Yet Oumuamua left no visible trail, no dust, no gas, just an eerie, silent speed boost that left scientists scrambling for explanations. The theories flew as fast as the object itself. Maybe it was a hydrogen iceberg evaporating invisibly in sunlight, or a fractal like a dust bunny from a distant protoplanetary disk, so porous it caught solar radiation like a sail. Then came the wilder ideas. What if it wasn't natural at all? Astronomer Avi Loeb famously suggested Oumuamua could be artificial, a discarded light sail from an alien civilization, or even a derelict probe. After all, its dimensions were oddly perfect for minimizing interstellar dust collisions, almost engineered. But here's the twist, we'll never know for sure. By the time we spotted Oumuamua, it was already racing away, too distant to chase. All we have are those tantalizing clues, a flicker of data from a fleeting encounter. And that's what makes it so haunting. If this was a natural object, it's unlike anything we've seen before. If it wasn't, well, that opens doors we're not ready to walk through. The real lesson of Oumuamua isn't just about one strange visitor. It's about how unprepared we are for the next one. Our telescopes are getting better, and within this decade, the Vera Rubin Observatory will scan the skies nightly, likely catching more of these interstellar drifters. Will the next one also accelerate mysteriously? Will it broadcast radio signals? Or will it just be another rock, reminding us that the cosmos is full of wonders we've yet to understand? One thing's certain, the universe doesn't care about our expectations. It keeps sending envoys from the void, and each one whispers the same thrilling truth. We've only just begun to explore. KIC 8462852, better known as Tabby's star, doesn't just flicker. It plunges into darkness like nothing else in the cosmos. Imagine a star that occasionally loses up to 22% of its brightness, as if a celestial hand were turning a dimmer switch at random. This isn't the gentle, rhythmic dip of a planet passing in front of its sun. This is erratic, dramatic, and utterly unexplained. When astronomers first spotted its bizarre light patterns in data from the Kepler Space Telescope, they knew they were looking at something unprecedented. Theories exploded like supernova. Could it be a swarm of comets, thousands of them, orbiting in a chaotic dance that blocks the star's light in unpredictable ways? Maybe, but the scale defies belief. For comets to cause such extreme dimming, they'd need to be far more numerous than anything seen in our own solar system, and their debris should leave infrared traces we haven't detected. Then there's the dust hypothesis, vast clouds of fine particles drifting across the star's face. Yet even this doesn't quite fit. Dust scatters light in predictable ways, and Tabby's star's dips are too sharp, too irregular. Which brings us to the wild card, the idea that caught the public's imagination. What if the dimming isn't natural at all? Enter the Dyson sphere, a hypothetical megastructure envisioned by physicist Freeman Dyson decades ago. An advanced civilization, the theory goes, might build a vast array of solar collectors around their star to harness its energy. blocking light in irregular patterns as the structure takes shape. It's a tantalizing thought, one that turns Tabby's star into a cosmic detective story. Are we glimpsing the handiwork of beings far beyond our technological reach? But before we leap to conclusions, the universe offers a sobering reminder. Extraordinary claims require extraordinary evidence. Recent studies suggest the star's dimming might be caused by something more mundane, yet still mysterious, a ringed planet with vast, uneven debris fields, or a magnetic phenomenon we've never observed before. Even if the answer isn't aliens, it's still groundbreaking. Tabby's star is teaching us that stellar behavior can be far more complex than our textbooks assumed. Here's the real magic of this mystery. Whether it's undiscovered physics or evidence of cosmic engineers, Tabby's star is a beacon in the dark, showing us how much we still have to learn. Every time it flickers, it's not just a star acting strangely. It's the universe nudging us to look deeper, think bigger, and stay curious. Because out there, in the uncharted territories of space, the next great discovery might not be what we expect, but it could change everything we know. Some voids in space are like quiet neighborhoods, sparse, but still dotted with a few celestial houses. Then there's the Boötes Void, a cosmic desert so vast and empty it feels almost unnatural. Stretching 330 million light-years across, this region of space isn't just lightly populated, it's a staggering vacuum, containing only a handful of galaxies where there should be thousands. If our Milky Way were dropped into the Boötes Void, the nearest major galaxy would be so far away, its light would take millions of years to reach us. It's as if someone carved a sphere out of the universe and left behind almost nothing. So what could create such a barren expanse? One theory suggests it's the ghostly imprint of an ancient collision between universes, a bruise left behind in the fabric of space-time. Another idea points to dark energy, that mysterious force accelerating the universe's expansion, possibly stretching this region thin over billions of years. But here's the twist, even these explanations struggle to account for the void's sheer scale. If the universe formed more or less evenly after the Big Bang, how did this pocket end up so empty? Then there's the eerie possibility that we're seeing a flaw in the cosmic blueprint. Imagine the universe as a sheet of bubble wrap with galaxies clustered in the raised bumps. Most areas have a mix of bubbles and flat spaces, but the Boötes Void is like a popped section, an anomaly that shouldn't exist under standard models. Some scientists speculate it could be evidence of exotic physics, like quantum fluctuations frozen into the early universe, or even a portal to something beyond our current understanding. But the real mystery isn't just what caused the void, it's what's happening inside it. Those few galaxies that do call it home behave strangely, drifting slower than expected, as if the void itself is resisting the universe's expansion. It's like watching leaves float in a tar pit, their motion defying the wind. Could this hint at unknown forces at work, or is it a clue that gravity itself acts differently in such extreme environments? The Boötes Void isn't just a curiosity, it's a challenge. Every time we try to explain it, the universe whispers back with more questions. Whether it's a relic of multiverses, a sign of undiscovered physics, or just a cosmic accident, one thing's clear. In the grand tapestry of space, some threads are still missing. And that's where the adventure begins, because the gaps in our maps aren't just empty spaces, they're invitations to look deeper. The outer solar system is a graveyard of clues, scattered with icy bodies that move as if something massive is pulling at them, something we can't see. Enter Planet 9, the hypothetical giant that could be lurking in the darkness beyond Neptune. This isn't just another Pluto-sized object. We're talking about a world up to 10 times the mass of Earth, orbiting so far from the Sun that a single year there could last 20,000 of our own. Its existence isn't just a hunch. The evidence is written in the odd, clustered orbits of distant objects like Sedna and other trans-Neptunian bodies, all tilted and stretched in ways that defy the gravity of the known planets. But how could something so big remain hidden? Think of it like a game of cosmic hide and seek. At such extreme distances, sunlight is feeble, just a bright star in an endless night. Even a planet this large would reflect almost no light, and its orbit could take it hundreds of times farther from the Sun than Pluto. Telescopes have only recently become sensitive enough to scan these depths, and even then, it's like searching for a charcoal briquette in a pitch-black warehouse. Theories about Planet Nine's origins are just as intriguing as the hunt itself. Some suggest it's a fugitive, a rogue planet captured by the Sun's gravity during the solar system's chaotic early days. Others argue it's a primordial survivor, formed much closer to the Sun before being flung outward by gravitational tugs from Jupiter or Saturn. There's even a wild possibility that it's not alone, that our solar system's outer reaches could harbor multiple unseen worlds, each shaping the dance of distant ice dwarfs in ways we're only beginning to map. The search is far from easy. Every winter, astronomers race against the clock, using the world's most powerful telescopes during the brief window when the suspected orbital path is visible from Earth. Each scan could be the faint dot moving against the stars that confirms we've found the solar system's last giant. And if we do, the implications are staggering. Planet 9 wouldn't just be another entry in the planetary roster. It would force us to rethink how solar systems form, how planets migrate, and whether our own cosmic neighborhood is far stranger than we ever imagined. For now, it remains a ghost, a gravitational echo in the data, a shadow in the math. But the hunt isn't just about finding a planet. It's about proving that even in our own backyard, the universe still holds surprises. And whether Planet 9 is out there or not, the search itself is a reminder. Sometimes the most exciting discoveries aren't the answers we expect, but the questions we never thought to ask. One moment, the radio telescope's readout is silent. The next, an explosion of energy more power than the Sun emits in 80 years blasts across the cosmos in less time than it takes to blink. This is the enigma of fast radio bursts, some of the universe's most baffling signals. These flashes, lasting mere milliseconds, arrive from galaxies billions of light years away, packing enough punch to outshine entire stars. And just like that, they're gone, most without a trace, leaving astronomers scrambling to decode their origins before the static swallows them again. What makes these bursts so mesmerizing isn't just their power, but their unpredictability. Some, like FRB 1211-2, repeat at irregular intervals, flickering like a cosmic lighthouse with no discernible pattern. Others fire once and vanish, as if the universe pressed a button and then forgot where it left it. The randomness has fueled wild theories. Could these be the death cries of neutron stars collapsing into black holes? Or maybe the aftershocks of cosmic strings, hypothetical defects in spacetime snapping like overstretched rubber bands? Then there's the spine-tingling possibility that we're hearing something far more deliberate. Imagine an advanced civilization harnessing the energy of a star to power interstellar beacons, their messages encoded in pulses too fast for us to decipher. It's not as far-fetched as it sounds. In 2017, astronomers noticed something peculiar about FRB 1211-2's repeating bursts. The signal's dispersion, how its frequencies spread out during their journey, had a mathematical precision, almost as if engineered. Of course, natural explanations exist, like plasma clouds in distant galaxies bending the radio waves. But the coincidence is enough to make even the most skeptical scientist pause. Yet the real breakthrough came when we started tracing these bursts back to their homes. In 2020, researchers pinned FRB 1800-916 to a spiral galaxy 500 million light-years away, nestled in a region of star formation. That location hints at Magnetar's ultramagnetic neutron stars as potential culprits. These stellar corpses, spinning at dizzying speeds, could unleash eruptions of radio energy as their crusts crack under unimaginable magnetic strain. But here's the catch: not all bursts trace back to such environments. Some emerge from quiet corners of the cosmos, where no obvious cosmic fireworks should be happening. The hunt for answers is accelerating. New telescopes like CHIME scan the sky daily, catching hundreds of these elusive bursts. Each detection peels back another layer of the mystery, revealing clues about the universe's hidden structures. Some bursts arrive with a twisted polarization, suggesting they've traveled through powerful magnetic fields. Others come with echoes, hinting at turbulent clouds of plasma between galaxies, a cosmic fog we've barely begun to map. Fast radio bursts aren't just cosmic oddities. They're probes illuminating the invisible threads weaving the universe together. Whether they're natural phenomena or something more, one thing's certain: every time one crackles through the void, it's not just a signal, it's a challenge. A reminder that the universe is still whispering its secrets, waiting for us to listen closer. What if death isn't the end, not even for stars? Meet the cosmic undead, stellar remnants that refuse to fade into darkness. These zombie stars cheat annihilation through physics so extreme it bends our understanding of reality. Take supernova imposters, for example. Some massive stars appear to explode in violent eruptions, only to rebuild themselves years later, like celestial phoenixes rising from their own ashes. In 2009, astronomers watched in disbelief as star SN 2009 IP flared brilliantly, faded, then erupted again years later, defying the finality we expect from stellar death throes. Then there are the vampires of the cosmos, white dwarfs that refuse to cool into black dwarfs. Instead, they siphon material from companion stars, triggering runaway nuclear reactions on their surfaces. These periodic explosions, called nova, can blast the same white dwarf back to life dozens of times, but the most extreme zombies are the magnetars. Born from supernova, these neutron stars should fade into quiet obscurity. Instead, their incomprehensibly strong magnetic fields, quadrillions of times Earth's, twist and snap, unleashing bursts of energy that temporarily resurrect them as blazing X-ray beacons across the galaxy. What makes these undead stars so revolutionary isn't just their defiance of the stellar life cycle. They're cosmic laboratories for physics we can't recreate on Earth. When a white dwarf reignites, its surface briefly simulates conditions like the early universe's quark-gluon plasma. Magnetar quakes may generate gravitational waves with patterns unlike anything from black hole mergers. Some theorists even suggest certain zombie stars could harbor strange matter, a hypothetical form of matter where protons and neutrons dissolve into a soup of free quarks under the crushing gravity. If proven, it would mean these stars aren't just dead things walking their entirely new states of existence. The implications ripple far beyond astronomy. Understanding how stars cheat death could reshape our search for extraterrestrial life. A reignited white dwarf might briefly warm frozen exomoons, creating transient habitable zones where none should exist. Magnetar flares could sterilize entire galactic sectors, or paradoxically spark probiotic chemistry in their aftermath. Even the universe's expansion rate might need recalculating if certain zombie supernova we use as cosmic yardsticks aren't the standard candles we thought. Perhaps the most humbling lesson these stellar undead teach us is about cosmic time. A human lifetime is too short to witness most celestial events, but not these. Watching a star die and resurrect within decades reminds us the universe isn't static. It's a dynamic, sometimes violent place where even the rules we think are absolute might just be waiting to be rewritten. And that's the real magic. The cosmos doesn't just follow scripts, it improvises. And in those improvisations, we find the clues to everything we don't yet understand. One August evening in 1977, a radio telescope in Ohio picked up a signal that would become the most tantalizing mystery in the search for extraterrestrial intelligence. It wasn't a faint blip or a garbled wisp, but it was a sharp, powerful burst of radio waves, 72 seconds long, blaring at a frequency that natural cosmic sources rarely emit. The astronomer monitoring the data, Jerry Amon, circled the printout in red pen and scribbled a single word beside it: "Wow." And just like that, the wow signal earned its name and its place in history as the closest we may have ever come to hearing from another civilization. What made this signal so extraordinary wasn't just its strength. It matched almost perfectly with the frequency of hydrogen, the most common element in the universe. Hydrogen's radio signature is often called the universal calling card because any technologically advanced species would recognize its significance, making it an ideal frequency for interstellar communication. The signal also originated from the direction of the constellation Sagittarius, where telescopes have since identified several exoplanets orbiting within the habitable zones of their stars. A cosmic coincidence, maybe, but the precision was uncanny. Yet here's the twist: despite decades of searching, the signal never repeated, not once. Astronomers have scanned the same patch of sky countless times, using increasingly sensitive equipment, but the silence has been deafening. If it was a deliberate transmission, why wouldn't whoever sent it do it again? Some argue it could have been a one-time beacon, a brief flare of energy, perhaps from a dying civilization's last effort to reach out. Others suggest it might have been a natural phenomenon we still don't understand, like a freak burst from a comet's hydrogen cloud or an unknown stellar flare. Then there's the unsettling possibility that we missed our chance. Radio signals disperse over interstellar distances, and even a powerful transmission would weaken into noise after light years of travel. What if the wow signal was a fleeting moment in a much longer message, one we only caught a fraction of? Or worse, what if it was repeated but we weren't listening at the right time? The universe doesn't operate on human schedules, and a civilization light years away might broadcast in patterns we can't predict. The wow signal remains a riddle wrapped in static, a whisper from the void that refuses to be explained. But its legacy isn't just about whether it was aliens or not. It's a reminder of how vast and unpredictable the cosmos truly is. Every time we point a telescope at the stars, we're not just searching for answers, we're stepping into a conversation that might have been going on for billions of years. And somewhere out there, in the uncharted depths of space, another signal could be waiting. The question is, will we be ready when it comes? Imagine an invisible hand sculpting the universe, pulling galaxies into shape, weaving cosmic webs, and bending light like a prism in empty space. That's dark matter. It doesn't glow, absorb, or reflect light, yet its gravitational fingerprints are everywhere. Take the Bullet cluster, for example. When two galaxy clusters collided, their visible gas clouds slammed together and slowed down, but something kept racing ahead, tugging stars along like an unseen locomotive. That something was dark matter, proving it's not just an idea, it's real, and it's holding the cosmos together. But here's the puzzle. If it's everywhere, why can't we catch it? Scientists have turned entire mountains into detectors, like Italy's Gran Sasso lab, where ultra-sensitive instruments wait for a dark matter particle, maybe a WIMP, or weakly interacting massive particle, to bump into an atom. So far, silence. Others hunt for actions, hypothetical particles so lightweight they'd stream through lead like ghosts through walls. Yet decades of searching have turned up empty-handed. Could we be chasing shadows? Some theorists argue the problem isn't the matter. It's the math. Modified Newtonian dynamics, or MUND, suggests gravity might behave differently at cosmic scales, eliminating the need for dark matter entirely. But MUND struggles to explain phenomena like the cosmic microwave background's intricate patterns, where dark matter's influence is etched into the universe's oldest light. The debate isn't just academic. If dark matter is real, it could be a gateway to undiscovered particles and forces, a whole new branch of physics hiding in plain sight. Then there's the eerie possibility that dark matter isn't uniform. What if it clumps into hidden structures, invisible planets, stars, even galaxies? Simulations show dark matter halos where these shadowy objects might form, drifting unseen through space. Could there be entire dark matter civilizations forever cut off from the light-bound universe? It's a wild thought, but that's the thrill of this mystery. Dark matter isn't just missing mass, it's a cosmic riddle that challenges everything we think we know about reality. And solving it might not just reveal what's out there, it could redefine what matter itself truly is. Picture a moon so vast it dwarfs entire planets, circling a gas giant in another star system, an exomoon with icy geysers erupting into space and hidden oceans churning beneath its frozen crust. These distant worlds could be the most promising places to hunt for life beyond Earth, yet spotting them is like trying to find a firefly next to a floodlight. The challenge: their parent planets outshine them by thousands of times, and their subtle gravitational tugs are lost in the cosmic noise. But the hunt is on, and the stakes couldn't be higher. Take Kepler 1625b, a Jupiter-sized exoplanet with a curious wobble in its transit data, a hint that something massive might be orbiting it. Scientists suspect this gravitational hiccup could be caused by an exomoon the size of Neptune, a behemoth with its own atmosphere and possibly even liquid water. Then there's the tantalizing case of Kepler 1701b, where astronomers observed unexpected dips in starlight that didn't match the planet's rhythm. The best explanation: a moon trailing behind its host world, casting its own faint shadow as it passes between the star and our telescopes. But what makes these moons so special isn't just their existence, it's what they might hide. Imagine a super Europa, a moon 10 times the size of our solar system's icy ocean world, with tidal forces from its giant planet keeping its subsurface seas warm enough for life. Or an exomoon with a thick nitrogen atmosphere, like Titan but warmer, where hydrocarbon lakes could host chemistry we've never dreamed of. The ingredients are all there: water, heat, organic molecules. The only thing missing is proof. Detecting these hidden worlds requires cosmic detective work. Astronomers look for telltale signs like transit timing variations, tiny delays in a planet's orbit caused by the gravitational pull of its moon. Others hunt for moonlight itself, filtering out the blinding glare of the host star to spot the faint reflected glow of a lunar surface. It's painstaking, like listening for a whisper in a hurricane, but the payoff could redefine our understanding of habitable zones. A planet too close to its star might be scorched, but a moon at the right distance from its gas giant could enjoy the perfect balance of warmth and protection. And then there's the ultimate question: if life thrives on one of these moons, how would we know? Future telescopes might analyze their atmospheres for biosignatures, oxygen, methane, or even industrial pollutants hinting at intelligence. But for now, exomoons remain ghostly possibilities, their secrets locked in data streams and mathematical models. Every flicker of light, every irregularity in a planet's orbit could be a clue. The universe is teeming with worlds beyond worlds, and we're just beginning to learn how to see them. For decades, whispers have swirled about a shadowy object silently circling our planet. Not just any piece of space junk, but something far older and far stranger. The so-called Black Knight satellite has been called everything from an ancient alien probe to a relic of lost human technology, its origins shrouded in static and speculation. The story begins in the late 1950s when amateur radio operators reported picking up eerie, delayed echoes of their own signals, as if something unseen in orbit was bouncing them back. Then came the grainy photos, dark, irregular shapes captured by early astronauts, floating against the blackness of space. Scientists have long dismissed these accounts as misinterpretations. The echoes, likely ionospheric disturbances. The photos, debris from early space missions or thermal blankets lost during spacewalks. After all, Earth's orbit is cluttered with over 100 million fragments of human ingenuity, discarded rocket stages, dead satellites, even a lost glove. But here's where the mystery deepens. Some of these Black Knight sightings predate humanity's first forays into space. In 1899, Nikola Tesla claimed to have intercepted strange rhythmic signals while experimenting with his Colorado Springs wireless transmitter, sparking theories that something artificial and not of this world was already up there listening. The most compelling twist lies in the object's alleged orbit. Unlike most satellites which follow predictable paths, the Black Knight is said to move in a polar orbit, a trajectory rarely used by early spacecraft due to its complexity. Even stranger, polar orbits are ideal for mapping the entire planet, leading some to wonder, was this object placed there intentionally to observe us? Modern radar scans have yet to confirm its existence, but that hasn't stopped enthusiasts from scouring old mission transcripts and declassified documents for clues. Could the truth be hiding in plain sight? In 2018, SpaceX's Falcon Heavy launched a Tesla Roadster into space, its cameras briefly capturing an unidentified object drifting nearby. Conspiracy forums erupted. Was this the Black Knight finally revealing itself? Astronomers quickly identified it as a piece of the rocket's fairing, but the moment underscored how easily the unknown can spark our imagination. Whether the Black Knight is a cosmic myth or a forgotten piece of history, its legend taps into something deeper, our fascination with the idea that we're not alone and that the skies above might still hold secrets older than we dare to guess. Until definitive proof emerges, it remains a ghost in the orbital machine, a reminder that even in our own backyard, the line between fact and folklore is thinner than we think. Near the event horizon of a black hole, time doesn't just slow, it stretches like taffy, warping seconds into centuries. Imagine a civilization perched on the edge of this gravitational abyss. While their world crawls forward at a glacial pace, the rest of the universe races ahead. In the time it takes them to brew a cup of tea, entire empires rise and fall beyond their distorted bubble of spacetime. This isn't just science fiction. Einstein's theory of relativity tells us that extreme gravity bends time itself, creating pockets where the past might linger like a cosmic fossil. Think about what that means for lost relics of the universe's infancy. Near a supermassive black hole, objects from the dawn of creation could remain virtually untouched, preserved in slow-motion amber. A primordial gas cloud, a cluster of first-generation stars, even artifacts from a long-dead alien culture. All of them might exist in a state of suspended animation, shielded from the ravages of time by the black hole's crushing grip. Astronomers have already spotted ancient stars orbiting Sagittarius A, the supermassive black hole at our galaxy's center. Could there be even older secrets hiding in those swirling depths? The implications are staggering. If we could probe these regions, we might glimpse the universe as it was billions of years ago, like tapping into a cosmic time capsule. Picture a probe sent too close to a black hole's edge. To observers on Earth, its signals would redshift into oblivion as time stretched infinitely. But from the probe's perspective, millennia would pass in a blink, offering a front-row seat to the universe's distant future. The catch: there's no coming back. Any data collected would be a one-way message whispered across the ages. Then there's the eerie possibility that black holes aren't just preservers, they're creators. Some theories suggest that under these extreme conditions, exotic matter or even entirely new physics could emerge. Particles trapped in time loops, quantum echoes of ancient events, or structures forged in the fire of the Big Bang itself. It's as if black holes stitch together the universe's oldest and newest threads, weaving a tapestry where time is just another variable to bend. The hunt for these cosmic relics isn't just about curiosity. It's a race against entropy, a chance to touch the universe's memory before it fades entirely. And every black hole we study, every warped photon we analyze, brings us closer to answering the most profound question of all. Are we alone in time, or just one thread in an infinite tapestry of civilizations, each frozen in their own moment of history? At first glance, space appears as a vast, silent void, but the closer we look, the more we realize it's anything but empty. What seems like nothingness is actually a turbulent quantum sea, where particles flicker in and out of existence so fast they defy detection. This isn't poetic metaphor, it's hard science. Heisenberg's uncertainty principle tells us that even in a perfect vacuum, energy fluctuations create a froth of virtual particles, constantly appearing and annihilating in bursts of raw potential. It's as if the universe itself is breathing at a scale we can't see. Now imagine tapping into that energy. The vacuum of space isn't just seething with particles. It holds enough latent power to theoretically boil away entire oceans in the blink of an eye. Physicists call this the zero-point energy field, and while we can't yet measure it directly, its effects are undeniable. The Casimir effect proves it. Place two uncharged metal plates incredibly close together in a vacuum, and they're inexplicably pushed toward each other. Why? Because the quantum foam outside the plates has more energy than the restricted space between them, creating a measurable force from what we once called nothing. The implications are staggering. If we could harness even a fraction of this energy, it could revolutionize space travel. Picture an engine with no fuel tanks, just a device that extracts propulsion from spacetime itself. No more chemical rockets guzzling finite resources. Instead, ships might ride quantum fluctuations like surfers catching a wave, crossing interstellar distances without carrying a single drop of fuel. Some theories even suggest this energy could warp spacetime, bending it to create shortcuts between stars. A real-life warp drive straight out of science fiction. But here's the catch: the energy is locked away tighter than a vault. These quantum fluctuations happen on scales a billion times smaller than an atom, lasting fractions of a nanosecond. Capturing them would require technology we can barely conceive of, materials that don't yet exist, controls for forces we're still struggling to understand. Some researchers propose using ultra-cold superconductors or lasers to tame virtual particles, while others explore exotic matter configurations that might stabilize tiny wormholes. The wildest possibility, this quantum foam might hold the key to time itself. Certain solutions to Einstein's equations suggest that intense zero-point energy could twist spacetime into loops where cause and effect break down. It's a long shot, but not impossible, like finding out the empty air around us was hiding electricity all along. So the next time you look up at the night sky, remember, the darkness isn't empty. It's alive with possibilities, crackling with energy we're only beginning to glimpse. And somewhere in that quantum chaos, the universe might have left us the ultimate toolkit if we're clever enough to reach for it. What if every choice you've ever made spawned an entirely new universe? The multiverse hypothesis isn't just science fiction, it's a serious scientific proposition with roots in quantum mechanics and cosmic inflation. Picture this: our universe might be one bubble in an endless cosmic foam, where each bubble operates under completely different physical laws. In one universe, gravity could be 100 times stronger, making stars burn out in mere millennia. In another, electromagnetism might be so weak that atoms never form, leaving behind a swirling sea of subatomic chaos. The evidence comes from unexpected places. When scientists study the cosmic microwave background, the afterglow of the Big Bang, they find strange anomalies that standard physics can't explain. Some regions appear slightly colder or hotter than they should be, as if they're brushing against other universes in dimensions we can't perceive. Then there's quantum mechanics, where particles exist in multiple states until observed. The many worlds interpretation suggests every possible outcome actually happens. You just experience one branch while alternate versions of you live out every other possibility in parallel realities. But how would we ever detect these other universes? Some theorists propose looking for bruises in space, places where our cosmos might have collided with another, leaving imprints in galaxy distributions or radiation patterns. Others suggest hunting for gravitational anomalies where the fabric of space-time seems to tug in directions that defy our universe's geometry, the most mind-bending possibility. Black holes might actually be portals to these alternate realities, their singularities stitching together different cosmic membranes in ways we're only beginning to model mathematically. The implications are staggering. If the multiverse exists, our most fundamental constants, the strength of gravity, the mass of electrons, might not be carefully tuned for life at all. We could simply be in one of the rare universes where conditions happen to allow our existence, while countless others remain barren. It's like winning a cosmic lottery where most tickets are blanks. Yet for all its grandeur, the multiverse hypothesis remains controversial. Critics argue it's untestable philosophy dressed up as science. After all, if other universes are permanently beyond our reach, how can we ever prove they're real? But supporters counter that absence of evidence isn't evidence of absence. 500 years ago, the idea of unseen planets orbiting distant stars seemed equally absurd. The multiverse might be the next great frontier, waiting just beyond the edge of our telescopes and our imagination. Ancient astronomers mapped the heavens with nothing but their eyes and stone tools, yet their celestial records still leave modern scientists speechless. Take the Nebra sky disk, a 3,000-year-old bronze artifact from Germany depicting the Sun, Moon, and Pleiades star cluster with uncanny precision. Or consider the Dogon people of Mali, whose oral traditions described Sirius's invisible companion star centuries before telescopes confirmed its existence. How did cultures separated by oceans and millennia decode cosmic secrets we'd need satellites to verify? The answer might lie in patience we've long since forgotten. Imagine generations of skywatchers tracking Venus's 8-year cycle across temple doorways, or Mayan scribes noting lunar eclipses in codices so accurate they're still used to calibrate modern astronomical models. At Chichen Itza, the Pyramid of Kukulkan casts a shadowy serpent that slithers down the steps precisely during equinoxes, a feat requiring architectural genius married to celestial mechanics. These weren't just observations, they were conversations with the cosmos, written in sunlight and stone. But here's where the mystery deepens. Some ancient records contain anomalies that defy easy explanation. Babylonian clay tablets mention a great star near Jupiter that modern astronomy can't account for. Chinese texts from 60 BC describe a guest star lingering near Alpha Centauri for months before vanishing. No supernova remnant exists there today. Could these be glimpses of celestial events we've never witnessed? Or perhaps evidence of lost worlds, planets, or stars that met violent ends long before our telescopes turned skyward? The most tantalizing clues come from what these cultures chose to emphasize. While we fixate on planets and galaxies, ancient astronomers obsessed over the spaces between the dark rifts in the Milky Way that Inca cosmology called celestial rivers, or the aboriginal songlines tracing interstellar dust clouds invisible to the naked eye. Modern infrared telescopes now reveal these regions as stellar nurseries and black hole hubs. It's as if our ancestors sensed the universe's hidden architecture long before we had the tools to see it. Perhaps their greatest lesson isn't in the stars themselves, but in how they watched. Without light pollution or the distraction of digital screens, they perceived subtle shifts we'd miss today, the dimming of a star now known to harbor exoplanets, or the flicker of a variable star like Betelgeuse long before its erratic behavior made headlines. In chasing the next big discovery, we might have lost the art of seeing the sky as a living, breathing entity. The past whispers that the cosmos still holds surprises for those willing to look not just with lenses, but with wonder. Deep in the cosmos, two city-sized stars spiral toward each other at nearly the speed of light. Each so dense a teaspoon of their material would weigh 1 billion tons on Earth. This is the prelude to a neutron-star collision, one of the universe's most cataclysmic and creative events. When these stellar corpses finally collide, the explosion unleashes enough energy to outshine entire galaxies for a few blinding seconds. But the real magic happens in the aftermath, where forces so extreme they warp the very fabric of reality, forge elements we treasure here on Earth. Take gold, for instance. That ring on your finger or the wiring in your phone likely originated in a neutron star smash-up billions of years ago. Ordinary stars can't create heavy elements like gold or platinum. Their furnaces lack the necessary power. But during a neutron-star merger, the insane pressures and temperatures reaching trillions of degrees rip apart atomic nuclei and reassemble them into exotic isotopes. Free neutrons bombard lighter elements in a rapid-fire process called the R process, building up gold atom by atom in a cosmic alchemy that would make medieval chemists weep with envy. Scientists estimate a single collision can produce hundreds of Earth masses worth of precious metals, scattering them across the galaxy in glowing debris clouds that eventually seed new solar systems. Yet these collisions don't just manufacture bling, they're gravitational wave factories. When the stars finally merge, their immense masses churn space-time like a spoon stirring honey, sending ripples across the cosmos at light speed. In 2017, the LIGO Observatory detected gravitational waves from such an event for the first time, accompanied by a gamma-ray burst and a glowing kilonova, a multi-messenger astronomy triumph that confirmed theorists' wildest predictions. But the real surprise came when telescopes analyzed the afterglow. The light spectrum revealed signatures of heavy elements forming in real time, proving these crashes are the universe's primary forges for elements beyond iron. Now here's where things get truly bizarre. Some models suggest neutron-star collisions might briefly create conditions so extreme they birth strange new states of matter. At densities beyond imagination, protons and electrons could merge into a sea of quarks, a primordial soup not seen since the universe's first microseconds. Others speculate about hypermassive neutron stars, temporary remnants so dense they hover on the edge of collapsing into black holes, their interiors possibly harboring exotic particles or even microscopic wormholes. We're talking about environments where the laws of physics as we know them start to break down, offering glimpses into realms beyond the standard model. The implications ripple far beyond astrophysics. If these events produce stable, strange matter, a hypothetical form where quarks roam freely rather than being locked inside protons, it could transform our understanding of the universe's fundamental building blocks. There's even a fringe theory that some ultra-dense asteroids in our solar system might be fragments of neutron star crust, delivering alien matter to our cosmic doorstep. Every time astronomers spot another merger, they're not just watching a distant explosion, they're witnessing the universe's recycling program in action. The gold in your jewelry, the uranium powering reactors, even the iodine in your thyroid, all were likely forged in these violent, beautiful collisions. It's a humbling thought. The remnants of dead stars don't just light up the cosmos. They built the very elements that make our bodies, our planet, and our technology possible. And somewhere out there, another merger is brewing a cosmic pressure cooker, ready to mint new elements and hurl them into the void, where they might one day become part of worlds and lives yet unborn. Beyond Neptune's orbit, the solar system doesn't just fade into darkness, it erupts into a bustling highway of icy worlds, each one a frozen time capsule from our cosmic dawn. This is the Kuiper Belt, a sprawling disk of primordial debris stretching billions of miles into the void. Most of its residents are modest chunks of rock and ice, but a few defy expectations with bizarre orbits that twist like pretzels across the sky. Take Sedna, for example, a reddish world locked in a 12,000-year orbit, so elongated it never comes closer than 76 times Earth's distance from the Sun. What slingshotted it out there? The answer might rewrite our solar system's history. Then there's the curious case of the Kuiper Cliff, a sudden drop-off in objects around 50 astronomical units from the Sun, as if someone drew a cosmic "do not cross" line in the ice. Some theorists suggest an unseen planet's gravity could be sweeping the area clean, while others propose the debris simply never formed that far out. But the most tantalizing clues come from the way certain Kuiper Belt objects cluster together, their orbits tilted at similar angles like synchronized swimmers. Computer simulations show this choreography could be the handiwork of a Mars-to-Earth-sized world lurking in the darkness, a true Planet 9, not just a mathematical ghost. What makes these distant ice balls so revolutionary isn't just their odd behavior. They're pristine relics from the solar system's construction yard, untouched by the heat and collisions that reshaped the inner planets. When NASA New Horizons zipped past Arakoth in 2019, it revealed a snowman-shaped world so perfectly preserved that its two lobes showed barely any impact craters, a snapshot of how planetary building blocks gently stuck together 4.5 billion years ago. Other Kuiper Belt objects might harbor even bigger surprises, like subsurface oceans kept liquid by radioactive decay, or exotic ices that don't exist anywhere closer to the Sun. The next generation of telescopes could turn these hints into revelations. The Vera Rubin Observatory's decade-long sky survey will track millions of Kuiper Belt objects, potentially spotting the gravitational fingerprints of hidden worlds. Proposed missions like the Interstellar probe aim to plunge straight through this frozen frontier, mapping its composition in ways remote sensing never could. And somewhere in that data might lie the answer to astronomy's most humbling question: are we missing a whole chapter of our own cosmic neighborhood story? Because the Kuiper Belt isn't just a graveyard of ice, it's a puzzle box. Every odd orbit, every unexplained gap whispers about forces we've yet to discover. Whether it's unseen planets, interstellar visitors captured long ago, or structures left over from the Sun's birth cluster, one thing's clear: the solar system doesn't end where our textbooks say it does. It just gets stranger. Galaxies aren't the solitary giants they appear to be, they're cosmic predators. Over billions of years, the largest galaxies grow by consuming smaller neighbors, tearing them apart in a process astronomers call galactic cannibalism. The Milky Way is no exception. Right now, it's in the act of digesting at least a dozen dwarf galaxies, their stars stretched into shimmering ribbons known as stellar streams. These ghostly trails, like the Sagittarius stream looping around our galaxy, are the cosmic equivalent of crumbs left behind after a feast. But what if those crumbs hold more than just stars? What if they're all that remains of lost civilizations swallowed by our galaxy's hunger? Consider the Gaia sausage, a collection of stars with wild, chaotic orbits that stands out sharply against the Milky Way's orderly spiral. These stars aren't native, they're the mangled remains of a dwarf galaxy our Milky Way devoured 8 to 10 billion years ago. If life arose in that galaxy, even briefly, its traces might still drift among us. Imagine a planet from that long-dead system, ejected during the collision and now wandering the Milky Way as a rogue world. Frozen and dark, it could harbor the ruins of cities or the faint echoes of radio signals sent by a species that vanished before Earth's continents even formed. The math is sobering. Over its lifetime, the Milky Way has likely absorbed hundreds of smaller galaxies. Each merger would have sent shockwaves through their stellar populations, flinging planets into the abyss or hurling them into new orbits around unfamiliar stars. Some might have been lucky, a habitable world tossed into the Milky Way's suburbs, its biosphere surviving the upheaval. Others could have been sterilized by radiation from newly formed supernova, their histories erased in an instant. Yet the most haunting possibility isn't just the loss of these civilizations, it's how close we might be to finding them. Advanced telescopes like Gaia are mapping the motion and composition of billions of stars, flagging those with unusual chemical signatures that betray their foreign origins. A planet orbiting one of these stars, rich in elements uncommon to our galactic neighborhood, could be a smoking gun. Even more telling would be an artifact, a derelict probe, a beacon, or some other engineered object drifting in the void, waiting to be spotted by our surveys. Galactic cannibalism isn't just a violent spectacle, it's a cosmic recycling program. Every star we see, every world we discover, might carry fragments of a history far older than our own. The Milky Way's past is written in the trajectories of these stolen stars, and if we learn to read them, we might uncover stories not just of annihilation, but of survival. Imagine the universe as a frozen lake in the deepest winter, seemingly smooth until you look closer and see the cracks. Cosmic strings are like those fractures in the ice, but instead of forming in water, they're defects woven into the very fabric of spacetime itself. These hypothetical relics from the universe's birth are thought to be thinner than a proton, yet they could stretch across the entire cosmos, carrying the weight of entire galaxies in their gravitational wake. If they exist, they'd be like invisible wires strung through reality, bending light, distorting time, and possibly even stitching together the edges of parallel universes. The idea emerged from the chaos of the Big Bang. As the newborn universe expanded and cooled, physicists believe it underwent phase transitions, like steam condensing into water, but on a cosmic scale. Just as ice forms cracks as it freezes, space-time might have developed flaws where these transitions didn't align perfectly. These flaws wouldn't dissipate. Instead, they'd persist as cosmic strings, vibrating like guitar strings plucked by the universe itself. The energy trapped in just 1 centimeter of such a string could rival that of a mountain range squeezed into a thread a billion times thinner than a human hair. What makes these strings so revolutionary isn't just their bizarre properties, it's how they'd warp reality around them. Picture a string passing near a star. Its immense gravitational pull wouldn't just bend the star's light, it would split it, creating double images like a celestial funhouse mirror. If two strings crossed, they might snap violently, sending ripples through space-time so powerful they'd distort the shape of entire galaxies. Some theories even suggest these collisions could birth new universes, popping into existence like bubbles in a cosmic foam. The hunt for cosmic strings is already underway, using tools both ancient and cutting-edge. Pulsars, the universe's most precise clocks, could betray a string's presence if their rhythmic signals suddenly stutter as space-time wrinkles pass by. The faint afterglow of the Big Bang, imprinted in the cosmic microwave background, might bear scars from strings slicing through the early universe. And then there's LIGO, the gravitational wave observatory that could detect the tremors of a string vibrating like a plucked wire somewhere in the void. Yet the most tantalizing possibility isn't just finding a string, it's what we could do with it. Some models suggest these defects might be stable enough to act as cosmic shortcuts, bending spacetime so severely that traveling alongside one could let us cover interstellar distances in the blink of an eye. Others warn that a close encounter might unravel the very laws of physics in its vicinity, creating zones where matter behaves in ways we can't predict. Whether they're out there or not, cosmic strings challenge our understanding of reality itself. They remind us that the universe might not be the smooth, orderly place we assume, but a patchwork of imperfections, each holding secrets from the moment of creation. And if we ever find one, it won't just be a discovery. It'll be a doorway to a new frontier of physics, where the threads of spacetime itself are waiting to be pulled. In the vast emptiness between stars, where sunlight fades to a dim glow, two robotic explorers began behaving in ways that defied all expectations. NASA Pioneer 10 and 11 spacecraft, launched in the early 1970s to study the outer planets, became the center of one of spaceflight's greatest puzzles. As they hurtled toward interstellar space, mission controllers noticed something bizarre. Both probes were slowing down slightly more than physics predicted, as if some unseen hand was gently tapping the brakes. This tiny discrepancy, just a fraction of a nanometer per second squared, became known as the Pioneer anomaly, and it would haunt scientists for decades. At first, engineers assumed it must be an onboard issue, perhaps leftover propellant slowly leaking from the craft's thrusters, or heat radiating unevenly from their nuclear power sources. But meticulous calculations ruled out these explanations. The deceleration remained stubbornly present, consistent across both spacecraft despite their different trajectories. The numbers suggested an additional force acting on the Pioneers, one not accounted for in our understanding of gravity or spacecraft mechanics. Theorists scrambled to explain it. Could it be the gravitational tug of undiscovered matter in the outer solar system, or perhaps evidence of dark matter's subtle influence on our cosmic neighborhood? Some even proposed radical modifications to Einstein's theory of gravity itself, suggesting our laws of physics might need rewriting at interstellar scales. Then came the plot twist. In 2012, after years of painstaking data analysis, a team discovered that thermal radiation from the Pioneer's plutonium power sources emitting heat asymmetrically from their dish-shaped antennae could account for most of the anomaly. The very energy keeping the probes alive was also, in an ironic twist, pushing them off course. Case closed, not quite. While this explanation fits the bulk of the discrepancy, some researchers argue there's still an unexplained residue, a whisper of something else at play. What makes the Pioneer anomaly so captivating isn't just the mystery itself, but what it reveals about how we explore the unknown. Here were two spacecraft built with 1970s technology, accidentally uncovering questions that still resonate today. Their unexpected behavior forced us to scrutinize every assumption, from the way heat flows in zero gravity to the fundamental nature of gravitational forces in the outer solar system. Even if the anomaly has been mostly explained, its legacy endures as a cautionary tale. The universe loves to surprise us, often in ways too subtle to notice until we're halfway to the stars. Perhaps the greatest lesson lies in what we haven't found. The pioneer's journey showed us that deep space isn't just an empty highway, it's a realm where even the smallest deviations can hint at hidden truths. Whether it's undiscovered physics, elusive dark matter, or just a quirk of thermal radiation, their story reminds us that exploration doesn't end when a probe leaves the solar system. It's just the beginning of a deeper conversation with the cosmos, one where the answers often raise more questions than they settle. Most stars drift lazily through the galaxy like leaves on a pond, but not these. Hypervelocity stars are the cosmic speed demons of the Milky Way, rocketing through space at millions of kilometers per hour, fast enough to escape our galaxy's gravitational grasp entirely. Their origins read like something from an astrophysical thriller. Picture a binary star system, two stars locked in a graceful orbital dance, wandering too close to the supermassive black hole at the galaxy's heart. In a flash of gravitational chaos, one star gets captured, while the other is slingshot outward at unimaginable speeds, like a stone flung from a catapult. This isn't theoretical. Stars like S5 HVS1, discovered racing through the constellation grooves at nearly 6 million kilometers per hour, bear the mathematical fingerprints of such a violent expulsion. But black holes aren't the only cosmic cannons capable of launching these projectiles. Supernova, the universe's most powerful explosions, can kick companion stars into the void with a single, asymmetrical blast. When a massive star detonates, the sheer force of its death throes can send nearby stars careening into the darkness, their trajectories forever altered. These stellar refugees often carry clues to their violent pasts in their chemical compositions, abnormal levels of heavy elements forged in the supernova's furnace, or scars from the shockwaves that propelled them. What happens to these rogue stars once they're set loose? Some tear through interstellar gas clouds, leaving glowing bow shocks in their wake like the wake of a speedboat. Others, like the infamous He0 437 5439, move so fast they'll eventually escape the Milky Way entirely, destined to drift through the abyss between galaxies for eternity. Imagine a star alone in that unimaginable darkness, its light visible to no civilization, its warmth touching nothing. It's a haunting thought, but also a thrilling one. These intergalactic wanderers could be carrying the seeds of future solar systems, their ejected material eventually coalescing into planets in a galaxy far from their own. The hunt for hypervelocity stars isn't just about cataloging cosmic oddities. Their paths are cosmic breadcrumbs, tracing back to some of the most extreme events in the universe. By studying their speeds and trajectories, astronomers can map the hidden gravitational landscape of the Milky Way, inferring the locations of dark matter concentrations or even undiscovered black holes. Every hypervelocity star is a messenger screaming its story across the light years, if only we're quick enough to catch it. Black holes dominate our cosmic nightmares, regions where gravity wins so completely that not even light escapes. But what if the universe has an opposite? Enter white holes, the theoretical antithesis of their dark siblings. While black holes devour everything that crosses their event horizons, white holes would violently expel matter and energy, spewing it outward in a cosmic eruption that nothing could enter. These bizarre objects emerge as valid solutions to Einstein's equations of general relativity, yet they've never been observed. The question isn't just whether they exist, it's whether the universe could even sustain such a violation of the usual flow of time and matter. Imagine a celestial fire hose blasting out particles and radiation with enough force to reshape entire galaxies. Unlike black holes, which form from collapsing stars, white holes would theoretically emerge from the same math but run backward in time, like a movie of a black hole's formation played in reverse. Some physicists speculate they could be the other end of a black hole's tunnel, a hypothetical exit point via an Einstein-Rosen bridge. Picture matter swallowed by a black hole in one corner of the cosmos, only to be vomited out light years away by a white hole. It's a compelling idea, but here's the catch. White holes violate the second law of thermodynamics, which dictates that entropy or disorder must always increase. A white hole's sudden outburst of organized energy would essentially reverse this arrow of time, creating a paradox that makes most cosmologists skeptical. Yet the universe loves exceptions. One tantalizing possibility is that white holes aren't permanent structures but fleeting phenomena, cosmic burps from the early universe. During the Big Bang's unimaginable violence, conditions might have been so extreme that pockets of spacetime briefly behaved like white holes, ejecting primordial matter before settling into the laws we know today. There's even a fringe theory that certain gamma-ray bursts, those blinding flashes of energy detected across the universe, could be the death throes of microscopic white holes evaporating in a final, catastrophic outburst. The hunt for evidence is as tricky as the math. Since white holes would repel rather than attract, they'd be nearly impossible to detect unless one happened to be actively erupting in our cosmic neighborhood. Even then, their signatures might mimic more mundane events like supernova or quasar eruptions. But if we ever did confirm their existence, the implications would rewrite physics. White holes could challenge our understanding of causality, force us to rethink the nature of singularities, and even offer clues about the birth of the universe itself. For now, they remain ghosts in the equation's mathematical curiosities that tease us with the possibility of a universe far stranger than we've dared to imagine. Whether they're out there or not, white holes remind us that the cosmos still holds mysteries not just in the uncharted voids, but in the very laws we thought we understood. And sometimes the most radical ideas aren't just science fiction, they're puzzles waiting for someone to prove them real. One of the greatest puzzles in modern astronomy isn't hiding in the distant cosmos, it's baked into the very fabric of our measurements. Scientists call it the Hubble tension, and at its core lies a simple but unsettling discrepancy. The universe appears to be expanding at different rates depending on how we measure it. On one side, we have the cosmic microwave background, the afterglow of the Big Bang, suggesting an expansion rate of about 67 kilometers per second per megaparsec. On the other, observations of nearby supernova and variable stars peg the number closer to 73. That gap might seem small, but in the precise world of cosmology, it's a chasm wide enough to shake our understanding of reality. So what's causing this rift? One possibility is mundane but critical: measurement errors. Imagine trying to time a race where one stopwatch runs slightly fast and another slow. The Hubble constant, named for Edwin Hubble, who first proved the universe was expanding, relies on complex calibration chains. Astronomers use standard candles like Cepheid variable stars, whose predictable brightness variations let us gauge distances, and Type I, a supernova, which explode with consistent brilliance. But what if our candles aren't as standard as we thought? Dust might dim them unevenly, or their physics could vary subtly across cosmic time, skewing the results. Recent debates over the exact distances to the Large Magellanic Cloud, a crucial calibration anchor, show how delicate this web of measurements truly is. Yet if the tension persists even after refining our tools, the implications are staggering. It could mean our universe isn't just expanding, it's evolving in ways we don't yet grasp. Some theorists propose dark energy, the mysterious force accelerating cosmic expansion, isn't constant but growing stronger over time. Others speculate about early dark energy, a surge of repulsive gravity in the universe's first moments that left fingerprints in the cosmic microwave background, subtly altering its predictions. Then there's the radical idea that we're seeing hints of extra dimensions or undiscovered particle fields bending space-time in ways Einstein's equations never anticipated. The most tantalizing possibility, the Hubble tension might be a signpost pointing to a deeper layer of cosmic structure. Just as quantum mechanics emerged from tiny discrepancies in atomic physics, this rift could reveal new laws governing the universe's grandest scales. Future telescopes like the James Webb Space Telescope and the Vera Rubin Observatory will scrutinize these measurements with unprecedented precision. Whether they close the gap or widen it further, one thing's certain: the cosmos is nudging us toward a frontier where the answers might rewrite the textbooks. And that's the beauty of the tension. It's not just a problem to solve, but a doorway to discoveries we haven't even imagined yet. From rogue planets adrift in eternal night to the invisible threads of dark matter weaving through the cosmos, these unsolved mysteries aren't just gaps in our knowledge, they're invitations. Every time we uncover a cosmic anomaly, whether it's a star that shouldn't exist or a gravitational tug with no visible source, we're reminded that the universe is far stranger, far richer than our textbooks dare to suggest. Think of each enigma as a locked door with no keyhole. We can't even see what's on the other side yet, but the mere fact that the door exists means there's territory beyond, waiting to be mapped. Consider how far we've come. A century ago, we didn't know galaxies existed beyond our own. 50 years ago, black holes were mere mathematical quirks. Today, we're capturing their silhouettes and listening to space-time ripple with their collisions. The mysteries we grapple with now, the nature of dark energy, the origins of fast radio bursts, the true scale of the multiverse, will one day be foundational knowledge for future generations. And just as those before us turned speculation into science, we're standing on the threshold of the next revolution. The tools are already in our hands: gravitational wave detectors tuning into cosmic symphonies, telescopes peering deeper into the infrared, algorithms sifting through petabytes of data for patterns no human eye could spot. Yet for all our progress, the greatest lesson these uncharted territories teach us is humility. The more we learn, the more we realize how much lies beyond our grasp. That's not a failure, it's a gift. A universe that could be fully understood would be a prison for curiosity. Instead, we're blessed with endless frontiers, each mystery a spark that ignites new questions, new technologies, and new ways of seeing. So keep looking up, but not just with telescopes. Look up with wonder. The next great revelation might come from a backyard stargazer tracking an anomaly, a student spotting a pattern in old data, or a probe sending back images that rewrite the rules. The cosmos doesn't discriminate in how it reveals its secrets, and if history's any guide, the truths waiting out there won't just expand our understanding of space, they'll reshape our understanding of ourselves. The adventure's far from over. In fact, it's just getting started. Hit subscribe and let's uncover the next cosmic mystery together, because the universe isn't just a place to explore. It's a story we're all writing, one discovery at a time.